Is it a good time for you? Okay. Who's traveling over the holiday, Thanksgiving holidays? Oh, you're not traveling. You're gonna study. You're gonna work on home. Seriously, if you're not gonna travel. Wow. Okay. How are things with the homework? Is it doable so far? Haven't looked at it yet. Probably. Who cares about homework until the last minute? Questions from previous class? Everything is crystal clear. Completely grasped. Okay. So okay, let's do it. So this week. Oh, by the way, before we start, next week. Next week is the first week of October. Is that right? You don't want to communicate today. Did something happen? You absolutely refuse to communicate. So next week, Monday, you don't want to see me, right? Yes, good. And Wednesday, I don't want to see you. So that means that next week we're not gonna have lectures. Okay, I'm traveling to Japan, so no way I can give a lecture. So next Wednesday we won't have a lecture, and we will see how to make it up. Okay, so Wednesday we don't have a lecture. What you mean 4th of October? Is it 4th or 3rd? Yeah, 4th. Yes, that's right. Yes. Yes, 4th of October, we won't have a lecture. We will post an announcement again. Okay, on the KLMS, you will receive an email too. Questions? Okay, so we will finish up the canonical organization, and we will talk about the first encounter of infinities in quantum field theory. And then we will move on to the story about the symmetry, known as the Noether theorem. Okay, so we're going to spend time with symmetries, this, and then the week after next week. Okay, and then after that, we will start developing machinery to be able to deal with the non-interacting quantum field theory, not just the free propagation, but if you have interactions, now something can happen, right? Two things can collide, produce something. So we start developing machinery to be able to handle those situations. Okay, but again today, and then second week of October, we will learn how to think about symmetries, which is extremely important. And in fact, one of the reasons we passed on to the Lagrangian formulation rather than talking about causality, is because there symmetry is not manifest. Okay, how would you even talk about symmetry? But Lagrangian formulation allow you to talk about symmetry in a very clear way. Even without Lagrangian, still we can talk about symmetry, but it's easier and it's in a sense streamlined to talk about symmetry, and we're going to spend time on it. Okay, so let's do it. So in the first 20 minutes or so, we're going to wrap up what we started, but then hopefully we will see a comparison between previous discussion about the causality and construction of a consistent field and so on, and Lagrangian formulation that we've been doing so far. Okay, we will see the matches. If you feel comfortable with that, then we can move on. If not, it's your problem. I'm sorry. I don't think I can help you. Okay. Anyway, let's do it. So what we talked about, so we start talking about classical field theory. Then we quantize it. So for instance, we talked about action, which now in addition to time, that's sum over this, so that it is a manifest Lorentz invariant way of putting time and space together. And then we say, okay, let's define Lagrangian density, which can have a function of a field. There are several number of them, and then in this case, like first is derivative of a field. Then we say, okay, obviously, hopefully you remember, you haven't forgotten everything, that that thing is what we traditionally call Lagrangian. And hopefully let me remind you quickly again that the way you want to think about, if you're confused, is if this corresponds to still what a dynamical variable that we are interested in understanding time evolution of, and that there are possible discrete labeling and continuum labeling, right? But then we just write this way, and we now have an interpretation or physics picture of a field. Now, what we do was that, well, we did a canonical quantization. quantization by first passing to what? Hamiltonian density from the Lagrangian density, which is possible by doing this. Now I'm not gonna bother to write how you read this equation again. I think I repeated it enough. Right? Once you get there, what do you get now? You get now you get to impose what? Canonical commutation relations. Which is, again, I'm not writing this, but otherwise I can say equal time commutator. Right? That's what I mean. Whenever I write this, cyclically I mean x, comma t, y, comma t with the same thing. But in general, you can say it that way because we learned that Lorentz transformation led you always to this rank. More crucially, we have to impose. Let me write this. Right? In fact, there was a rule. I mean, this was literally nothing but a Poisson bracket of variables. From this, then, what we get is that we can get a dynamical equation, which is Heisenberg operator equation of motion. In this case, it was what? Like phi dot as an operator. Right now you promote it to. This is an operator. Has to satisfy what comes first? 8. 30. Nice. And then we can also write this. Or for that matter, for any operator, you can construct out of that variations, right? Okay, then I showed that in the case of free scalar field, so the example of a free scalar field where at some point, by the way, I'm gonna start writing down this and this. If that doesn't look completely absurd to you at some point. Okay, but for a while, be careful. Because that seems to be absurd from your favorite bread line. Anyway, so then we showed at least for this example, if we actually apply this machinery of passing from the classical field theory to non-quantum field theory, right? We get that actually operator equation, which is nothing but plain order equation. Okay, as a Heisenberg equation of motion, not classical equation of motion. So we got an operator equation. Good. Minus sign somewhere? No,
n square has to be plus sign. I see.
No, I don't like that. Do I like that?
You wrote in that last week.
That's what I put?
Yes.
Did I put minus sign? I plus. Do I like it? Yes, I like it. Thanks. Good. Okay, so you can do it. Now, once again, I stress that this is not operator equation. So at this point, let's collect what we have achieved. We never asked the question about the causality, unitary, blah, blah, right? Say, oh, I'm done, I'm just giving this slide, right? I'm gonna just follow this straight to the point, right? Without a single thought, you can do it, right? As a robot, you can do it. And then what you have gotten so far is that, so at this point, what can you do? Well, I can solve this operator equation of motion. I can impose this relation. So for instance, I already talked about this. You can solve it, and then you can get. You can solve it. You can get e to the minus beta s out of t. Remember, I first constructed, Fourier transform. I imposed reality, and then I inserted the 1 equal to, remember, theta of P0 plus theta of minus P0. Inserted it, right? And then I said, okay, solution is the same as having an expression of delta square that, and then change of variable, you combine this to get this, so on and so forth. I talked like that for a while ago. All right, now, okay. So anyway, so you can get this. Now this is operator equation. Now what you can do is, you will be asked, do it in the homework, second homework. Oh, is it too early to talk about second homework set? Did I make a mistake? I think I did, right? I made a mistake. So then it's the other way around. Now you say, okay, I just got the solution of it. Again, no brainer. I haven't even thought about consistency, blah blah. I just solved it. Then I shove this into equal time commutation relation, and you should get that, well, equal time commutation relation, including equations of motion. You should get that, oh, I learned. Not that I expected it, I learned now that it should satisfy this, and then alpha equal to 0, alpha dagger equal to 0. Okay, was it clear? This is given, you follow, you get the quantum field theory with equation of motion as a Heisenberg operator equation. And then you get the solution, and you determine what kind of commutation relation alpha dagger most satisfy in consistent with commutation relation of field. So everything starts from the field, you determine the rest of the structure, right? Good. So this is no-brainer way of passing on to the quantum field theory. We have done exactly the opposite, right? I say, oh, I know, because I'm thinking there should be many body problems, right? This is relativistic quantum mechanical. So I need to have this formulation. Ooh, I can construct a complete box fix out of it, right? And then I said, oh, that looks like, how do I understand? How they ask the question of causality? Well, I have to first pass on something that looks like the field. Then I can talk about the measure and the distance, blah, blah. And then I impose the 5 conditions, right? Reality, causality, this and that, and that, and that. And there's spent some time to derive this. And 2 of the ingredients were, I want to have this Klein-Gordon equation because every relativistic I must satisfy this. And then I want to have causal initial conditions, right? And then I can determine this structure. In this way, you have to think every single steps. Now you're completely no-brainer. Okay, so that's why we have established so far. But somehow it gives rise to everything completely consistent with all the deep principles, right, of relativity and quantum mechanics. Okay, is that clear? So now we're going to take this no-brainer question. Why? What's that? A, you can carry around all this deep concept with you, but if you try to carry around a deep concept, and then if you try to add an abstract deep concept, you're overburdened at some point. So now, given the fact that you know how to understand this problem, let's trivialize it by just following this path. Now we have a room. In your brain now have a room to add something more, right? So now I'm gonna add a story about the symmetry, that, and dynamics, this and that. I will start adding on more conceptual part of it. Okay? So now you go that way. Is that clear? And then now I can talk about fermions and vector bosons. I can add a lot more stuff. So that's what we have done. Okay, question at this point.
Then does that mean that just we can just automatically satisfy the causality and whatever, no problem? If you just use any, here's my Lagrangian, and yeah, the causality automatically satisfy.
Almost, but not quite. Not quite. That's why you know when this is invertible relationship. Your question is it always invertible?
Yes.
The answer is no. So if Lagrangian contains some nasty badass in it, like, okay, I'm gonna have constructed, this looks like totally manifest Lorentz invariant term. Let me edit, ask what happens to my theory. Either you can choose to be plus sign or minus sign, but that doesn't affect the lower boundedness of the Hamiltonian. But this, depending on the sign, one side you're dead, the other side you're happy. Where that come from is again coming from this causality and unitary. So there's this business of some higher derivative interactions, what is known as extremely dangerous. But this topic, I mean, this sort of understanding was achieved very recently, around the 2000, early 2000, 2000 or around the time. You see, people still start developing or understanding some possible constraints of the Lagrange term that again coming from this deep principle of causality unitary. So you want to know it, right? In case you need to analyze this problem by yourself. This type of business still going on today, still going on. It's called the positivity bound. Some of the what's known as a Wilson coefficient, meaning coefficient in front of some derivative operator, are constrained to be positive, coming from again unitary and causality. So your answer to your question, no. So depending on the theory, you have to be careful. Another question. Any other question? Okay, now let's meet our first infinity. I met the predicate. In fact, more than 50% of second part of the QFT is train yourself how to fight with infinities. Literally. Is this infinity good infinity? Is this bad infinity? If it is a bad infinity, okay. So it's called the renormalization business. And that's big chunk of the second part of the QFT. But here we're gonna learn it and we just say, okay, I'm cool with you. So don't bother me. We will just move on. So with this, let's actually compute it. Okay, let's just compute it. So scalar field theory, simple scalar, real scalar field theory, Hamiltonian looks like now. Oh, remember, we have written down this figure. Okay? So everything is positive, positive, positive. We're good. Now, by solving equations of motion, we construct this, we can shove into that expression and try to get the Hamiltonian in terms of creation analysis operators, right? You can do it. Now, what was the expectation though? What would be your expectation? When we were discussing all this business in the backward, right, from this point of the standpoint of view, our expectation was this: Hamiltonian is got to be, okay? Hamiltonian must be of the form that there is energy, and then this. So what was the intuition back then? We say every single point in the momentum space, there is a simple harmonic oscillator, right? And therefore, at each point of it, I can excite that guy creating that particle or not. So we can just count total number of particle excitations. We sum over all those energies for each of those particles. And that should be Hamiltonian, right? That was intuition. Now that was intuition or that was expectation. If you do it on the other hand, so from this path, if you do calculation, what you get instead, this is a straightforward calculation. You have to do some integration by part. You have to use some of the delta function and so on. I'm going to ask you to do it sometime. You should get the following answer. Okay, so this no-brainer path gives you this answer instead of that answer. Oh, by the way, let me remind you that this creation annihilation operator was related to, so this one was like, this one that satisfies this version of commutator, and then I used to use this notation so far, right? That one satisfies additional 2 pi to the cube and 2 times e delta, because this particular combination was Lorentz invariant combination. So I've been using manifestly Lorentz invariant combinations. So you see the relation between the two, right? There's a scale by cube root of that factor for each of those factors, right? That's the relationship between these two. Anyway, going back to this question, the reason why I'm writing this way, on the other hand, is this is more physical now, right? At each point P, I'm just gonna have energy. This is just number without having any 2E and so on. So I'm just gonna have a much more straightforward physics interpretation. That's why I decided to describe this way. Good. Now, okay, I know how to deal with this guy, so let me just do it. So this is equal to subtract and add. So that means if I subtract this factor from here and then add it again, the first piece will give you commutator piece. And then add. Is this good? Okay, good. So that thing is therefore delta of 0. What is delta of 0? Let's just write it out. So then this gives you what does it give you? It gives you a dagger a plus half of delta. Okay, that's hilarious infinity. There was a question about this, probably it was you who was asking about this. Okay, let's discuss the meaning of this. So how do we deal with this problem? Well, first of all, this is infinity, manifestly. Okay. That can also look pretty infinity too. So let's see how that works. So here, this guy actually has the two infinities. There are two different kinds of infinity in that expression. Is the math clear so far?
Yes.
Okay. So let's understand the meaning of it. So first, I'm gonna talk about the nature of infinity. Second, I will interpret physically where they come from, why we should expect such an infinity. Okay. So there are two infinities. There are UV and IR infinities or divergences. I'm not gonna teach you how to deal with it. I'm just gonna teach you how to recognize it. Okay? At least you see, oh, this is UV infinity, this is IR infinity. So let's see. So UV, first of all, means shortness. Or equivalently, that means the high energy. Therefore, this IR means that the long distance, or equivalently, this is low energy. So let's take a look at this expression and understand what I mean by that. So let's think about the term that is actually divergence. And then, well, there's half delta. Half doesn't play the role. All right, so let's first just zoom in this part first. Let's forget about that guy for a second. Okay, so just for a moment, let's just look at this piece. And energy, EP, is P squared plus M squared. So let's go to the regime where P is actually, so I have to integrate from 0 to infinity. So this is integration of entire path momentum, right? But let's just go to the very high momentum regime. And then in that regime, so as P goes to much larger than the mass, basically this can be approximated as the size of the P cell, right? Because P is over dominating the mass. That's what I mean. All right. So that means that this integration looks like, D3P. Okay, and super schematically, that just means the P in Q. Again, super schematically. But we can deal with it much more carefully, but just schematically. Let's pretend we're going to integrate this guy from 0 to some value lambda. Okay, up to factors of 1/4, whatever. You see that this goes like lambda 2. Okay, and then now let's say I have to integrate this back all the way up to the infinity. So that diverges like what? Infinity to the 4th. But the reason why I didn't say that, but I say this way is it is infinity, but it tells you how it is infinity. Right? It just shoots like a big number to the 4th power. So in technical terms, we say this is UV divergent because the infinity comes from large momentum region. Right? So it is UV divergence. And in fact, in this particular example, we say it's partially divergent. because it shoot up, balloons up like UV scale to the fourth power. Okay, so it's cortically divergent. Good. So that's the UV divergence that is captured or encoded in this single expression. Okay, this guy has a UV divergence. Very bad. But it also has an IR divergence. So let's look at this part now. Understand the meaning of that. Okay, so that, remember, is P minus P. So why is this IR divergence? So for this, in order to understand this case, first of all, let's understand its map. Let's see if you guys remember this map. Either plus minus. Up to 2 pi to the cube somewhere. Probably here, but I don't know why. Okay, so who knows? Somebody may sue me if I don't. So there's 2 pi to the cube somewhere, but I'm not taking responsibility. Okay. All right. So let's first understand the meaning of it. So first of all, divergence, we put it in this delta of 0 in momentum delta function. You have to put that in 0, so then use this, which is space-time volume. So the reason why this guy diverges is because space-time volume you're taking is infinitely large. But let's be more sharp. Let's be more sharp about the meaning of the IR divergence here. So let's first consider finite box. Finite box with volume B. At this point, the B is not infinity, but just the finite size of box. So in that case, what we do is that you can solve that Schrodinger equation. What you do? So P x L x is equal to 2 pi NS, right? Okay. Along the x direction, you have sinusoidal wave function. You have to impose boundary condition that it dies off because infinity. The boundary of it, this is the conjugation condition you get. Remember? So you have a similar equation for y and z. Y. And likewise. So you utilize. Now what I'm gonna do is the following. So when we do this integration, so first of all, let's consider for fixed momenta. For fixed momenta P, in other words, I'm gonna fix this. Okay? What it means is that in the momentum lattice, according to the picture of a box space, so for fixed momenta, what it means is the number of momentum mode that I have to actually look at is proportional to the size of the space. Okay? That means that the total number of modes in the three-dimensional box in the momentum space that I have to solve over when we try to construct this Hamiltonian is proportional to the volume of space and time. That's exactly where it comes from. Okay, so here's the picture. Here is my lattice size momentum. Okay, there's a P. I have to sum over the simple harmonic oscillator. Now this term, I can tell the physics meaning of it. If you recall, in the simple harmonic oscillator, that looked like this. So there's actual excitation energy and there's the ground state energy, 0-point energy. So if you have a simple harmonic oscillator at this point in the momentum lattice, obviously you're going to solve for actual excitation, which is particle excitation in this example. But in principle, the formula knows everything about it. So you actually have to sum of entire 0-point energy of every single point in the momentum point, okay, the lattice. So you have to sum over half of whatever 0-point energy. Now, how many of them? Well, that depends on the number of modes in the momentum space. For fixed momentum, the number of modes is proportional to the volume of space and time. So you have to have half times the volume of space and time. That's the amount of mode you have access to. That's exactly this diagram. This is IR divergence. Because infinity, it comes from because space and time is so large, therefore super low energy region. Okay? So therefore this the expression has both divergence. Yes.
So in the low energy limit, the P is very small, right? But the L is very becoming large, infinitely large, so the P and L should be just remain the same.
Good. Now the way I want you to think about it is the following. Even for super large momenta, there is a simple harmonic oscillator attached to that point. And there is a 0-point energy there. So for every choice of momenta, there is a simple harmonic oscillator, there is a 0-point energy sitting there. So this picture is exactly identical everywhere, especially 0-point energy. It's there regardless of size of the momentum you're looking at. Because the question is, okay, let me look at the 1 EV point. So there's a 0 point plus 1 EV excitation. Let me go to the 10 to the 19 EV point. Okay, you might say super UV, but what about the 0-point energy there? It's still half. It's just that the single excitation that you're creating is 10 to the 19 EV particle energy. But 0-point energy is still just half. Is that clear? So here, the exercise I was going to show is that for fixed P, because you're going to anyway sum over entire structure, but this 0-point energy story is exactly the same. So for fixed P, the number of modes you have to worry about. In other words, you see, this is the separation between the momentum lattice. As you increase the volume, they shrink. There's much more mode coming into the game. Okay, so there's more 0-point energy you have to sum over. So that's what I'm trying to tell you. Is that clear? Think about it. But I will hold here if you have any questions.
만약에 LX도 고정된 운동량이라면 PX가 고정되어 있는 건데 뭐 볼륨이 주어져 있다고 하면 LX도 고정되어 있는 거니까 NX도 한 개의 값으로 결정되지 않나요?
You're correct. So if we fix P, if we fix L, this is a fixed number. So, but then the way I talked about it is following. How do I sum over this thing? There are two ways of doing it. For fixed P, I have to sum over 0-point energy. And then I have to sum over P. This sum over P give you UV divergence that I talked about. For every single size of P, there is this 0-point energy you have to sum over. And then this is a double integration if you like. Is that clear?
Yeah.
So then here what I was saying, therefore I said, let's forget about summing over all possible 0-point energy. But let me just worry about summing over momentum direction. That shoots out like this, UV divergence. And then I said, I forgot about that direction. So let's fix the momentum. And then I realized that the number of mode, because at every number of each mode, there is 0-point energy. The total 0-point energy is going to be half times number of mode in that direction. And then I showed the number of mode is proportional to the volume. If volume is finite, that's going to be finite. If volume is infinity, that's going to be infinity. Exactly how? Like delta function infinity. Okay, largeness of space and volume is captured not random lambda to the some power, just delta function infinity. What? Did I answer your question or?
Yes.
Okay. Okay. Now we can ask how should we deal with this? You deal with this way. Done. Okay. So that's done. There are a lot of words I can attach to that. Energy is measured only difference. 0-point energy, let's worry about later. It's special relativity, 0-point energy doesn't take advantage of physical significance. Whichever one you like. Eventually, you want to learn exactly how to think about this. At this point, we are not there yet. Okay, so the vacuum energy, so was that too salty? The 0-point energy, there's a lot of subtleties. And one of the most difficult problems in the particle physics is understanding this problem. Okay, known as the cosmological constant problem. And nobody knows how to solve it at this point. But today, at this level, there's an emergency. Let me turn it on. Okay, unless somebody is very cold, feel cold. Are you okay with turning on AC? Okay. So let me go back to here. So 0 point energy, naively, right? We learned that the potential energy only what only matters then is the difference rather than the absolute value. How you can think about it? Well, say you want to fix the exact 0 point energy instead, but then if you boost it, okay, energy vary is not a Lorentz variant. Boost it changes, right? So depending on the frame, even the meaning of the 0 point changes. So there is no absolute sense of absolute 0 point. Now, when does it get a sense? When you cannot do the Lorentz transformation. When does that happen? When geometry is given by the God, meaning if there's a general relativity, there's a dynamics that fixes the geometry, and you can just flip around the spatial slice. Then it is fixed. Then it gets alive. Then you say, I have a meaningful guy here, vacuum energy. So in that context, we have to worry about it. That's why cosmology constant problem, question about this, always involves the GR. Okay, it's not just pure quantity definition. But here we're talking about special relativity, and I don't worry about this thing. So at this point, we don't have absolute meaning to the 0 point energy. We can drop it. I know it's not a satisfactory answer. It's not like I don't want to give you a satisfactory answer. I don't have. So if you have one, come to me, talk to me. We can work together. Good. But there is a slightly better, not slightly. There is a one operational way of achieving this thing not appearing there. So let me just talk about it, and then I'm going to switch gears to the symmetries. But if there is a question, I'm ready to answer. Well, I may not be ready to answer, depending on the question. At least I'm willing to listen. Okay. So another way of phrasing this question, this issue of infinity, is the following. When we take this no-brainer path, right, instead of backward, what it spits out, the quantum theory that it spits out, that the systematic spits out, is up to operator ordering, right? And probably I don't know whether it's gonna just give me that, then okay, I'm happy. Whether or it's just gonna give me this. Anyway, it is like 2 half times, 2 of them. So it's counting works. But the ordering may be just method like that. So canonical quantization condition, therefore, generates quantum theory up to operator ordering. Right? The ordering is not guaranteed. So what I mean by that, I don't know if I ever talked about operator ordering issue. We'll just spend 5 minutes to talk about it. So probably I talked about one, suppose the Hamiltonian had Q squared in the classical theory, right? And obviously if you pass on to the quantum theory, you expect that it turns into Q hat square. And Q hat square doesn't have operator ordering ambiguity because this is the same. On the other hand, if Hamiltonian has Q square, P square. Now it's less clear whether quantum version should be Q hat square, P hat square, or P hat square, Q hat square, or Q, P, Q, P, or P, Q, P, Q, whatever. Right? And these are all related. Modulo, these are all related to modulo some factors of Q hat, P hat, which is size of the order of I times H bar. I just introduced H bar just for the sake of it for now. Right? So these are equivalent up to this factor, but you can just flip around orderings by taking, putting into these factors. You see, therefore, that when we say there's a quantum theory, can I just pass on to the classical theory? So therefore, as known as classical limit is taken by H prime tending to 0. This is the classical limit. So in the classical limit, we say momentum, position, commute. Doesn't matter. So in classical limit, because this goes to 0, commuter is 0, these are all equivalent. In fact, we say classically, yes, I don't care which order. Quantum mechanical, on the other hand, they can make a difference because of this effect. So this is operator of operator ordering ambiguity. Now, there is a one operation or notation, if you like, what is known as normal ordering. So what is normal ordering? I don't know who invented it. So normal ordering is the following. Notation is if you already have an operator, so suppose O is an operator in the Hilbert space, or according to some point that acts on Hilbert space. The notation for the normal ordering is these two dots. Like this, colon, semicolon, colon, this is anyway, so this is called two colon one side. This is notation. So what's the meaning of it? What's the meaning of it? Meaning is the following. So let me first show you a couple of examples, and then I just give you that general definition. So if there is this expression alpha dagger, normal ordering says you have to write that way, meaning you send the annihilation operator to the right, creation operator to the left. Okay, you just literally rearrange the. Let me do another example. Let's do the normal ordering of this sequence of operators. Okay, so I say, oh, okay, I have to send all the creation guys to the left, and then annihilation to the right. So that is normal ordered. Yes.
Does normal ordering consider the time ordering relation between the same sort of operators?
Oh, good. So there's another ordering for the time ordering. There's a relationship between these two according to Wick's theorem. So we're gonna get there soon. But for now, not necessarily worrying about the time ordering at this point, which will appear at the level of quantum field, right? Here I'm just gonna introducing you one symbol. This is a symbol known as normal ordering. The rule is you send all the creation to the left, annihilation to the right. You might say, oh, there's ambiguity. No. Right? They all commute, there's no ambiguity. Right? So that's the rule. Now, let me say then that when I define a quantum Hamiltonian, if I demand that the definition of my Hamiltonian is half of integration of 3 pi square radian squared and square of square. But then if I say, oh, actually, my Hamiltonian is defined with normal ordering, you might say, where does it come from? I just say, telling you. Say if. Let's see what happens, okay? Then this is equal to, because I have done the calculation, I can write it as, right? These 3P, normal ordering, have A dagger, A, EP. The only operators are these guys, like these guys doesn't matter, the half and EP doesn't matter. They just come out. I'm gonna be extremely careful with slow because this is the first time. Okay, so this is no problem. Just say if Hamiltonian is given by this is what I mean. All right, so let's just look at it. So the first normal ordering said, okay, creation to the left. Oh, did I switch? Creation to the left, annihilation to the right. Done. The second one is already normal ordered, right? So then this comes out as it. Therefore, my final expression for the Hamiltonian will be happily. Did I drop you? Okay, so I bypass the appearance of this infinity. Now, I know when I first studied normal ordering business, I was like, what is that? I don't get it. But at least what I want you to grasp it today is that there is ambiguity when you quantize here. At least that much, can you get it? and you just naively try to pass on to it, there's at least ambiguity. Which one you do it. And different quantization may result in final quantum mechanical expression with a different order. Got it. For instance, canonical quantization is a one way of quantizing the classical theory, decide to speed up this particular combination. Right? Who knows? You have, Jack Higgs quantization, which I just cooked up. Good luck with that fight. I just avoided that fight. 3 times that minus whatever, half 1 times that thing. Who knows, right? So anyway, there's this ambiguity depending on how you quantize it. There's this normal ordering. There's what's known as a final ordering. There's this time ordering. We will look at, but this, I'm not telling you that this is what you have to do. I'm just telling you that there's this notation, which we are going to use in the rest of the course. Okay, there's this notation. And if I just apply the notation, I don't know why we're going to do it, but if we apply the notation, at least I hope you can see that this is what's popping out as a result of exercise. Okay? So don't be confused. I'm not saying that this is what you have to do. I'm just saying that let's see what happens if you do it. And I'm not giving you an explanation whether this is good or bad. Rather, I give you explanation how to understand this thing. Right? And then I told you that in the structure. All right, so that was my first 20 minutes of lecture talking about wrapping up the first part of the class. 15 minutes. So in the rest 30 minutes, I want to switch gears to the symmetries. Any questions before? Yes.
Well, that's the Dirac brackets are from the Poisson brackets, but when it's so, if in the classical limit, shouldn't that go to the Poisson brackets, not zero?
Oh, good. So that's correct. The question, by the way, was I said that the canonical quantization, the way canonical quantization works is that if the commutative quantum is I times h bar times Poisson bracket. The question is, if I take a classical limit, why am I not going back to the Poisson bracket structure? Rather than why did I say this is equal to 0? So I guess what I meant by that was, first of all, this is not correct. So this is taking like explicit classical limit. We will talk more about it. I'm not sure how much this course, but at least in the second part of the course, we will talk a lot about it. There's loop counting parameter business. But anyway, to address your question, indeed, the classical limit of that thing should be Poisson bracket. You can ask yourself, even in terms of Poisson bracket, what it means that the Q and P say doesn't commute in the language of Poisson bracket. But I guess what I meant in this language is that it is consistent. It is consistent in the sense that if I now beam-off this guy as a classical guy, then obviously QA, PA should commute as an expression. What it doesn't commute as an expression is if I actually do non-trivial operation on those guys, which is defined in terms of Poisson bracket. Meaning, remember, the definition of Poisson bracket is take the first function, take the derivative with respect to the Q, take the second guy, take the derivative with respect to the P minus the opposite one. Yes, in this case, it is non-zero, it's correct. But what I was trying to prove from this exercise is as a product of this guy, not as a commutator of this guy. What would happen if I take a classical limit? There's just C-numbered function of time. So it should be just that. Okay? But in that sense, I said it should just be commute as h value of 0. Yes. Oh, 2 questions. Let me address first and then.
그 노멀 오더링이 유니크한가요?
Yes. So if your question was, does normal ordering result in unique expression? The answer is yes. Modulo possible free computation that you can do.
근데 그 만약에 게이지 트랜스폼처럼 어떤 필드가 이제 다른 필드가 2개의 필드가 있고 그 2개의 필드에서 좀 이제 이어하는 정도를 바꿔서 그러면 그 경우에도 그러니까 A 대거의 정의가 바뀌어가지고
What do you mean by changing the definition of a dagger?
끝나고 다시 질문드리겠습니다.
Okay. All right. Yes.
So when we apply normal ordering in the Hamiltonian, the normal order of A dagger plus A dagger A
Yeah.
to A dagger A.
Yeah.
Then in this case, vacuum energy problem is vanishes.
But instead you have to explain why this is the right thing, right? So this is not a solution to the vacuum energy problem. It's just like a fact or observation that somehow if I just write things as normal order, okay, it doesn't, the infinity doesn't appear. But oh, this is great because I don't have to worry about it. But you have to worry why this is the right operational process to do, which we don't have answer. So it's trade-off. Yes.
Is the whole UV versus IR issue related to just drop off to the third term?
This term. So no, okay, good. So the question was, I mentioned the two different divergences, UV and IR, and then when I drop it, whether there is this fine cancellation between UV versus IR. No, I didn't say that way. I just meant that this guy has generally UV divergence and IR divergences, and I just said that when we do quantum field theory in the flat space and time, there's no absolute notion of energy. There's only a notion of differences of energy. So vacuum energy can be adjusted away. Basically, that's what I meant. But however, when you say there's a fine cancellation between UV versus IR, there's actually a technical term that is called UV-IR mixing. And this is an extremely intricate concept and extremely hard to understand and extremely hard to engineer a concrete situation where that happens. But that happens in the nature. One example is, oh, this is fun, so I have to say. So the UV-IR mixing phenomenon occurs black hole. So usually, if you put more and more energy into the space and time, then because of the Heisenberg uncertainty principle, you get a probe in a smaller length scale, right? High energy means a short distance. So if you want to probe smaller distance, you have to put higher energy into it. That's why we want to build super energetic colliders, right? Suppose we keep doing it. I'm gonna have energy more. Now 1000 TeV, 10 to the 15 GeV, 10 to the 19 GeV. Looks like I can probe extremely small scale. In fact, 10 to the 19 GeV is the scale what's known as the Planck scale. And presumably that is the highest energy scale where quantum field theory makes sense. You can ask what happened after that? If I put just one single drop more of energy, more than 10 to the 19 GeV, this thing now starts forming a black hole. It has so much energy that it starts forming a black hole. You can ask, let's keep doing it. Let's put more and more energy. At some point, the black hole becomes larger. You see, all of a sudden, I put more energies. I expect to see smaller scale. Rather, I start creating larger black hole. But put more, even larger black hole. So there's this weird, violation of the naive relationship that we would expect. That works all the way up to the Planck scale. After they start breaking down, and this notion is known as UV-IR. Okay. Any other question? Yes.
노멀 홀더링을 주면은 그 이제 백큐 에너지 텀이 없어지는 것처럼 보이잖아요. 그러면 노멀 홀더링이 하는 게 실제 그 갭에 기여하는 오퍼레이터가 따로 있고 백큐 에너지에 기여하는 오퍼레이터가 따로 있는데 그 중에 우리는 관심 없고 애만 보겠다라는 식으로 해석을 할 수가 있어요.
You can try to interpret that. So if I understood it correctly, somehow mathematically, if I just do normal ordering, all of the vacuum term drops out, only this term, which corresponds to the excitation energy rather than 0 point energy. So your question seems to be that whether the normal ordering is so smart and clever that somehow it knows about the distinction between the two, and so single out this term. If that was your question, maybe that's the secret of what's going on with that. But at the moment, I'm just using literally as a notation, and then what you have to do. I don't know whether normal ordering is always that, but definition is, you see, it already just speaks up that. Oh, I didn't tell you by the way one important thing. Probably it has something to do with what I just said. So you might say, why are we even doing normal ordering? Crazy shit, right? Why are we even doing this? One nice property of a normal ordered operator is that every normal ordered operator, if you look at the vacuum expectation value, is 0. So that is related to what you said, right? This thing doesn't accept anything that is sandwiched between vacuum. You see, why is that? Well, that sounds like a strong statement. No, you see, the definition is put every annihilation to the right. So you see that annihilation, right? And then conjugation of that equation is that is equal to 0. So we send all the creation to the left. So yes, in that sense, the definition of normal ordering does have this fact that it doesn't keep any like vacuum energy by construction, if you like. Good. Are you ready to let me move on to the symmetry story now? Okay. Do it. But if you still have questions, I have. Okay, but today's the most important part of the discussion was for you to understand going that way versus that way. I summarized, okay? Hopefully you correct that. And we will encounter another instance where we will talk about the causality versus unitary in a different context. Probably not this semester though. If you're really curious, you may want to register again. Well, by the way, I don't know whether I'm gonna teach you tomorrow, but I can choose to teach. So there, just to spoil. Should I not? Once you understand the meaning of loops and high order corrections and quantum mechanical stuff, unitary is very quantum mechanical. So it is captured by imaginary part of something. Causality is more relativistic. It turns out that the real part of that something captures the causality in the language of our dispersion relation. But anyway, so that's not the topic for today, or even this semester. So now we're going to move on to the next topic. Oh shoot. No, we are not. So I have to say one more thing before we move on. So far, no. So in the rest of the class, of course, we will deal with interactive QFT. So far, what we have done is to make sense of free QFT, starting from free scalar field, like free classical field. Now, but then now, suppose I write S0 as the thing that we've been dealing with so far. We map like real general field. Then I can start adding like to my action, the theory, extra terms. So there is this free part that does the discrete propagation according to the Klein-Gordon equation. Then I can add like terms like Q, or I can add terms like to the fourth. Okay. So now, instead of being called radic, this is a high order infield, and they describe interactions. So recall that what quadratic thing to do is that if you look at the correlation function of a field, like in the vacuum expectation value size, what it can do is that this guy can create a particle, and then you move to another space-time point and see whether that particle still exists there, right? So this has a picture that at point X of space and time, or Y space and time, you create a particle in the way and see at X, you still that guy, right? You still see that guy. So this has an ability to describe the free propagation. Now, if we introduce this sort of terms, extra terms, then let's see what this can do. So now at a single point X in the space and time, that means that three fields mix together. Right? 5, 5, 5. But this guy corresponds to having this type of interaction. Like two guys can be together and shooting out another two guys. So once we start having these sort of interactions, then we start having interesting phenomena. So let's see what happens, for instance. So suppose using this part of it, I can create a particle. There's a free propagation. Good, it's going. But then at some point in space and time, I can split into two using, for instance, phi to the cube interaction. There's a non-zero quantum mechanical probability for that. Well, you might say, oh, that's interesting, but this can keep happening. Sometimes, you know, this can another split into two, right? Or this can split into two, but you have to close up and go back again. Or at this point, you can do 4-point function. Like this can use phi to the fourth. Here I've been using phi cube, phi cube, phi cube. But then this guy can do crazy stuff too, like that. You see, if there is interaction which is higher order than quadratic, being quadratic in the field, I can start having a lot of interesting dynamics. Now you understand, for instance, if I have a cubic, the interpretation of this process is the following. Quantum mechanically, I prepare the two particles, phi, they meet each other, so I get a collision. When they collide, something stops propagating for a while, but then it starts splitting into many different particles, like 1, 2, 3, 4, 5. So 2 particles ended up in 5 particles, for instance. So non-trivial physical process can occur if you start adding this sort of interactions. And again, the goal is to understand how to do this consistently. That's the goal. But then before that, now let's just even add, how are we going to proceed from this point? So in the rest of this course, we are going to focus on regime where lambda and g, the coupling constant, what is known as coupling constant. Why are they being called a coupling constant? Because the chances for such a process to happen obviously is proportional to powers of g, right? If g is large, this can happen more often. Because if g is 0, that thing never happens, right? So the chances for those non-trivial dynamics to happen is proportional to the size of these parameters of the theory, hence they are called coupling constant. Although they are not constant. But again, that's. So we are going to consider this regime where coupling constant is, say, small. I put this quotation mark because some of them is actually a number, but some of them actually carries non-trivial energy dimension. We will talk about it, but that's why I just put this. But so therefore, what I mean by this expression so far is we're going to focus on the regime where coupling constant in the proper sense is very small. What do I mean by small? Being small here. What I mean was this or that, whatever interaction term. So let me just put interaction term being much less important than the quadratic. That's what I mean. Okay, so eventually we will determine full machinery to be able to make this sharper. But at this point, let's just accept as a colloquial statement. Okay, just as the word. If this is the case, then what I can do is the following. So by the way, in this region, we say that we're going to do perturbation here. We're going to take all the interaction part to be small perturbation to the propagating part. So in this case, what we can do is that, so S consists of free part and interaction part. But then what we can do is that when we quantize the theory, ignore S for a second. Because it's a small, I know it's a small effect. So let's just take the largest part when we start at the classical level. And then just quantize only the free parts, which we know how to do it, right? Passon and canonical quantization, well, we have done that, right? Heisenberg equations of motion, we get all of that. Then we say, interpret that, then this thing, now we see like this guy, that guy, this is a free field. So this sort of iteration you have seen, for instance, in solving some differential equations and or integral differential equations, iteration, iterative method, right? You just start from taking largest contribution first, deal with that, and then plug in that solution into the high order guy and see whether the correction happens to the final solution. Okay, it's exactly the same concept. So therefore, within the regime or realm of perturbation theory, knowing how to quantize the free theory is sufficient to make a progress here already, right? You just quantize, plug back in that quantum free operator into the interaction guide, and start having physical understanding and picture of what's happening there. Okay. Now, you can ask, is this all we need to worry about? I listed for a while. But there's many conceptual issues. So for instance, there's a question about the strong dynamics. Like what happens when coupling becomes large? How do we deal with that? It's all very important question, and the huge effort has been put in to understand what happens when this is large. Okay, in fact, anyway, so that's what I wanted to say before we end, before we move to symmetry. So it's over timing. So next time, what I'm gonna moving on to is we're gonna spend a lot of time developing these machineries. So, but then next time we're gonna talk about symmetry for a while, a little bit. And there is an important theorem known as Noether theorem. So here's a quick summary of what we will discuss when we meet next time. So Noether theorem is a statement that if there exists a continuous symmetry, then there exists observed currents. The form that there's this underlying equation. So this is a classical statement. So what do I mean by symmetry, first of all? Symmetry means that consider you take phi of x, and then you transform it into something in terms of original field, like it acts some symmetry parameter, I don't know, lambda. So you turn it into something. The example is, okay, here's a phi of x. Can I make smooth continuous translation? Yes, you can, right? Okay, this is the translation. This is an example of smooth continuous transformation. And then we're going to go through all of that. So, but then what about the continuous part? And continuous part means that this parameter, for instance, is a continuous parameter. It's a constant parameter, but it is a continuous parameter. And whenever there's a notion of a continuous symmetry, we have a notion of infinitesimal transformation. Which means that I can take A to be very small, for instance. I can talk about extremely small translation, right? Whenever symmetry is continuous, we can always talk about infinitesimal transformation. And the notion of a current will pop up by analyzing what happens to the system because of the infinitesimal transformation. And let me finish what I mean by symmetry. Symmetry, for now, means that there is action, which was a function of phi field. Symmetry means that if I do make a transformation, that thing doesn't change. Action doesn't change. That's what I mean by a symmetry. So if I do make continuous action on the field, this good thing is the same. Why is it good to be called a symmetry? So you can ask, what determines the physics, first of all? So ultimate definition of symmetry is that you do something to the system and the system doesn't change anything, right? In other words, here is some experiment going on. It shouldn't matter whether I view that way versus that way. Right? Otherwise, how can I take any scientific data? And also, if I do an experiment today, I should be able to see the exact same thing tomorrow. So there's a time translation invariance. Right? Otherwise, how can I believe the physics law that was created hundreds of years ago? Right? So therefore, there's a certain invariance of the physics feature. That is symmetry. But then I connect that to the definition of action being invariant. Why is that a good notion of being symmetry? So you got to remember that action determined by local random direction equations of motion, right? Quantization, quantum field, and so on. So if I get the same action, this will give me the same equations of motion, same canonical quantization, same quantum field, and so on and so forth. And the set of those data basically tell you how physics works. So therefore, it makes sense to be called a symmetry because this guy will give me exact same quantum theory with the same physics. This guy will give me the exact same physics, same quantum field, and so on. Okay, so that's why this is a good definition of a symmetry at the level of action. And we're going to pursue next time consequence of this feature. Then we will learn a lot about the symmetry next time. Question. All right. So once again, due date for the homework 1 is sometime next week. Okay. And next week we're not going to have lectures. I mean, basically Wednesday next week we will not have a lecture. Right? Other than that, so therefore we will meet 2 weeks from now. Okay, with that, that's all for today. I'm happy to address questions if you have any outside of the